Good afternoon. Welcome to the end of week one. Congratulations, we've made it. How's TAs and everything else going for you guys? Settling in for sort of kickoff term? Going okay? I've got a tentative schedule that'll be posted up later today as far as when I'm assigning people. Again, it's done randomly. Please take a look over the weekend. Get back to me if I've accidentally scheduled it on a day where there's a no-go for some point. The earlier we can figure that out, the better. Has anybody started looking at what kinds of papers you might think about presenting? I would start that now. Again, ideally, go from the ASAPs, target is figure out one of the journals that I sort of suggested at the beginning, so one of the mainstream journals, Chem, JAX, ACS Catalysis, something like that. And again, it's even better, especially for the graduate students, pick something that is relevant to the work that you're doing right now, because most of you either have a reaction that you're struggling with, methodology you're trying to do. If it's relevant to your own research project, awesome, right? So I think that that's definitely super useful. Where we left off last time is we've started, defining the language around what is in rate equations. We're going to start talking about mechanisms, just as a reminder for what we are talking about energy surfaces. This is the analogy that we use in first and second year. Putting together something is just like the steps that you've actually done for Lego block or IKEA, where the individual bond formations and transformations are what we constitute the mechanism. Remember, the language we put here is that a starting material to a product is our overall reaction. The individual steps that we take in between them, those are elementary steps, meaning what? Like if I say it is an elementary step, what is that definition that I'm implying when I say that? Well, yeah, the connection between these two goes through a single transition state. That's the implication we're saying. Elementary step has, this is where we can derive a rate equation exclusively off of that elementary step. And this is also where elementary steps have to obey by a lot more physics. There are basically zero order, first order, or second order. Unimolecular processes, bimolecular processes, those are possible. It is very unlikely to get a termolecular reaction, right? Like if we have a single transition state, we're going from here to there, requires 3 atoms to collide together at exactly the same time. Probability says that that becomes exceptionally hard. If we have 3 components that have to react together, it's way more likely that A reacts with B, intermediate, B reacts with C, so you have 2 steps in that process, so breaking things up. This is just back to if you've ever practiced organic reaction mechanisms, the 2-arrow notation. If you have to invoke a step that has 7 or 8 arrows all at the same time, you're probably talking about more than one fundamental elementary step. So those are our vocabulary. An overall reaction is the total balanced chemical equation, atoms in, atoms out, and you just make sure that this is just accounting. The mechanism is the steps that go between them. Intermediates are things that could exist. They can be more stable, less stable. They're just stuff between the 2 things we've defined. And again, the difficult things with some of this is it's all relative. It depends on what we care about as the starting material of the product, right? One of the hardest things about digging into reaction mechanism is perspective. Just because an intermediate happens to be something between what you started with and where you hope to go, that might be the most stable thing in the entire system, which means that's what you're isolating most of the time. So the outcome of a reaction, calling it product or discarded product, is really just a perspective. And catalysis is something that, or a catalyst is something that helps to influence or change the reaction mechanism. So everybody should be very familiar with this kind of a diagram. It's something that you guys have probably used, again, qualitatively, but we'll be coming back to it a lot because it helps you to ground outcomes. Using this language of like, this is the energy surface I have, is a really important thing for you to practice when you're starting to talk about hypotheses. When you make a statement like, this reaction worked better than that reaction, I got one product and not another, you should be able to go back to a diagram like this and articulate what you meant. And we'll practice this part as we go through it. But so quickly, everybody recognizes the energy difference here to here. That's our thermodynamics. That's talking about stability and isolubility of materials. Which way this equilibrium might be favored really comes down to the relative energy difference between the 2. Fundamentally, microscopic reversibility says what? Like if I say microscopic reversibility, what am I trying to imply about a diagram like this? Does everybody know microscopic reversibility when I say that point? What does it mean then? if you had to phrase it? Your buddy put a microphone up under your mouth and said, hey, what does this mean?
The way that I would like define it, like the steps required to create from the reactions to products are in our cases to create from the product.
Exactly. Time doesn't matter, right? Bond formation in one direction probably and has to follow the same thing backwards. And we're literally looking at something in absence of time, which means the actual energetic path we follow one way has to match the other. It also kind of means every reaction to some approximation is reversible. Energetically, it may not be likely. You could have, like, the combustion of a piece of paper is a reversible reaction. The problem with it is, you know, gas flies everywhere, containing it in a thing, reassembling CO2 by that same mechanism back into paper and oxygen is an energetic problem and one of, you know, containment rather than fundamental physics. The bond orders could mean that anything is reversible. So keeping in your mind that every reaction, at least to a first approximation, is an equilibrium. What we call irreversible is just something that has either transition states or energetic barriers in such a way that is so far favored on one side. So that's the kind of the fully classical version of the world. And this is where, again, DFT is awesome for this because in a computer you can run any reaction backwards that you want, right? Reality and experimental becomes harder. Second point, so this is talking about your distribution of products, which one is favored energetically. This is talking about your speed, how fast a reaction goes. It's your energetic barrier. So on this diagram, if you're making statements about I got one product instead of something else, and stability is part of your argument, you should be absolutely make sure that your diagram represents that it's a product distribution for energy of your products is why that distribution happens. As compared to this formed faster than that, okay, you're talking about a barrier problem, right? So using your statements and hypotheses in terms of selectivity, stability versus speed is really important when you start to draft these out. Have you guys ever, like, give me some examples of where you've maybe used this in your experiments. Have you measured things like rate constants, activation energies, product distributions, delta Gs? Can you think back to any experiment that might have allowed you to quantify, let's say, the energetic difference between these two that you might have done as an undergraduate lab? Probably have done at least one. Maybe not as a, like, I solved a delta G, but can you think of anything you might have did at any lab? Again, I'm guessing from all your backgrounds, but I'm pretty sure you guys have done a titration at some point, right? If you've done a titration, you've measured something to do with both quantity but also relative stability by adding a strong ass to a weak system to solve a pKa. That's fundamentally a measurement of something like this too. Everybody has done like a pKa calculation titration at some point? Yeah. Oh, yeah, okay. It's all good. But I'm saying, like, this is why it's kind of, I like to emphasize it. You're actually a lot more familiar with this than you think. It's a language that we use. We see it in first year and go, oh yeah, that, and then we kind of use it very loosely. It's a lot more helpful to kind of bring yourself back to this and sort of talk through. When we start having multi-step reactions, your surface gets more complicated. This is also where now the rate law of something that has more than one elementary step, this is where you need experiments, right? This is where we can no longer say the overall reaction here can immediately be drawn, we can immediately draw the rate law. And it's because of the intermediates that could be there and the relative heights. This becomes a data science problem where almost any possible energy surface without any other information could fit for a reaction. This is where we have to make other measurements. Something I want you guys to do over the weekend. Go download this paper, go read this paper. We will talk about this paper. This is actually from the Journal of Chemical Education, 1918. So this is a new problem. What's funny is we still have this argument. And again, this is something where it's kind of a limit of even our discussion. This is one of the papers I really like going back to because it kind of breaks down this idea of what the heck a slow step or rate limiting step is, especially in multi-step reactions. Because it becomes, as soon as we walk out of these very simple cases, like simple systems like 2 steps, it gets very hard to overly generalize it. So when we start thinking about a multi-step reaction and talk about a rate limiting step, again, back in your own language, what does a rate limiting step mean? Slowest step. Okay, slowest step. Again, go a little bit further. What's happening if I had a cascade like this, which do you think is the slowest step? First step or second?
The second one.
Okay, out to the room. Second step. Why?
The barrier is the highest.
Okay, so you're saying you would predict if you dump in a whole bunch of starting material, you're going to have some distribution between these two, right? You have intermediate and reactant. This is a higher barrier, so it's highest on the energy diagram. So if you imagine this was, let's say, an analogy, we're climbing a hill. You've got a whole bunch of hikers here. They're walking back and forth, back and forth, back and forth. That's the gross grind. Most people are like, nah, but there are some people that will continue up to the top. So welcome to Vancouver. Have you guys all done the gross grind yet? Everybody? Okay, I haven't yet either. So, but still, this is a big climb, right? The energy you have to do to get out to that one is going to be a bigger investment. And once you're done, you're taking the gondola down, right? Like you're not actually going back the other way. That's an easy kind of visualization. So that's what's called highest height. You're saying the overall energy barrier here is what dictates slowest step, okay? Can anybody give me a corollary argument? What if, I don't know if I've drawn it out, what if it looked like this? Starting here, no, sorry, one sec. If I had an energy diagram that looked like starting material, big jump, where this had a value, I'm just going to say that's 10, and this here is only 6. So overall, that's still highest height, but that energy barrier is fundamentally larger. Now what happens? No, again, discussion. So who says first step? Why? The individual steps, first step is a larger delta G double dagger. So you need, let's say, 10 units of energy to get over that first one. Okay, does everybody agree with that? Who says second step? Okay, why? Again, ground it in an analogy. Go back to the hiking one.
I mean, you're still going to get some hikers up to that second hill, but getting over the first hill, getting over the second hill is still going to be problematic.
It is, but what's an argument you could use that the second hill is still your rate limiting step? This key of the reaction is clocked based on the absolute barrier height. The overall here might be, it depends on where that intermediate is, but the overall, let's say, is that, right? You're saying this is kind of the observed delta G double dagger. Yeah, sorry. Okay. Fair. You know, that's something you can sit there and say, look, climbing that first hill, I was so tired, I'm sleeping in that on the mountain, and then I'll worry about the second hill, right? That's one possible way, yeah? Absolutely. If all I did is forget about the starting material product, if I only look here, so I exist here, that's where I drop into the surface. If that's my decision point, winded or not, I got an easy hill to go on to get back that way, or I've got more work to go forward. So that kind of be that's kind of sounds like the second step is rate limiting. Towards my product, the rate of formation of my product is still the decision of this guy to climb that higher hill relative to this hill, right? We're not saying that this step doesn't have some impact, but the thing that matters more might be the second step. The other part too, the hiking analogy, and this is really the point of this paper, all physical analogies suck when you're trying to do this, because if you're a molecule, you're not tired, right? There's no winded. If you had enough energy to clear this first barrier, why don't you have enough energy to keep on going in the overall system? Otherwise, that's just an equilibrium. Like, remember, the energy distribution of a system isn't an atom by atom point. It's the kinetic energy that's distributed based on the Boltzmann constant of vibrations in the entire system. Heating something up just doesn't take energy in indiscrete packages. It averages out where you have more molecules. Probability says there's more molecules of enough energy at the high end of the system, which just allows to get over these barriers. The quick answer is it depends. Like, there will be cases where the first step actually is the most important step, depending on where these heights actually lie. Sometimes, this is what comes down to what's an argument of fundamentals. It says what's called highest height versus biggest jump. Those are the two kind of camps you can look at it, where overall highest height is the thing that clocks which reaction happens or not. Biggest jump is kind of a rate problem of which step do you get over before some distribution actually happens. And it depends on the actual energy surface. That's one of the things they bring up in this one. The other analogy that people used to use for kinetics is things like traffic or flow. You know, if I was driving in a Maserati or like a Lamborghini, but I'm driving behind like a smart car that's low on batteries, it doesn't matter how fast I could go. I'm limited by that step in front of me, right? So you can kind of come up with these points where it's not the fundamental instability or energy of the step before it, it's whatever bottleneck you're staring at. And it can depend on the absolute energy surface you're dealing with. The other one's called a flow analogy, where you imagine, let's say it was water and I'm pouring water downhill. If I am pouring a lot of water at the top of the hill and I have a very large cascade of energy, I expect it to be a huge flow down to this bottom reservoir, and then a little trickle after that would say the second step is my rate limiting step. The problem with that analogy is water flowing downhill. It's very difficult to come up with the version of a reverse reaction. I can't, in that mentality, gravity goes only one way, and I can't like jump things back uphill. So a lot of the early kind of thought diagrams of how does this actually happen start to fall apart because there's not a physical reality that we can easily put our hands on. That's where modeling is very helpful. So here are examples where the flow analogy, this kind of downhill thing, start to fall apart. Yeah?
Does this mean that we can't just look at delta G double dagger, the bigger one?
The overall delta D double dagger will always influence product distribution. That is in all cases. So what I'm saying there is, let's say if I have some starting point and I'm considering blue product versus, let's say, purple product. So in this analogy, I'm going to drop molecules in right here, and then after that, it can choose, does it want to go one way or another? Now, if this is all you see, then this is something you should all be familiar with. Blue versus purple, if this is the only existence, I'm not showing you anything about transition states, what does thermodynamics say should be the major product at equilibrium? Purple, right? The lowest energy one, because what we're assuming there is everybody hops between all states and it's a probability distribution of energy. So we're probably saying thermodynamics is going to put all this stuff over there. If I then add a barrier and say, here is one barrier and here is another barrier, which one forms faster based on this analogy? Because, yeah, so we're saying that hopping over here is going to be faster than this way. Ultimately, on infinite time, purple's still going to win as long as there's still enough energy to go from blue back to red over to purple, right? If these barriers are high enough, you're going to get trapped over here because there's just not enough energy to retro back into it. But distribution, delta delta G, selectivity, is always this. It's the relative energy height between two different competing barriers. So if you said that if in a system which doesn't obey full equilibrium or full equilibration, if I'm at one step and I have to look, do I go left or do I go right? Delta delta G will always win, right? That's where delta G will, delta G matters from a which is faster sort of sense. But as the mechanism gets more complicated, there may be traps where things get held up in between. This is where things like what we call Curtin-Hammett behaviors. Those are where you can get selectivity differences, which are a combination of both kinetics and thermodynamics. It's not exclusively one or the other. So there's not like a hard and fast rule. There's not always comes down to, oh, delta G double dagger overall is going to dictate how fast the reaction is. Depends. The rate will always be, the actual clocking of product always comes down to some concentration times a constant of that highest barrier. The problem is, if I was moving, let's say, in this direction, the concentration of that key intermediate to clear that last height might be so vanishingly small because the first step is so bad. But you're right in the sense that I can always stare at just this step and say, in a perfect world, if I knew exactly that concentration, I would be able to tell you how fast product is forming because it's only that step. It's the step over to product that's at that highest barrier. The problem is populating that intermediate can be really difficult depending on what surface you need to get to it, right? So these are examples you guys have probably touched or run that follow this point. So carbocations, E1 type processes. So this is an example of a tosylate that has a fast equilibrium to make a secondary carbocation, not very stabilized, that then has to go through a really slow step of a capture of a nucleophile. So the relative energy diagram you should have in your head for this looks kind of like this. You've got a fast equilibrium to some high energy intermediate, and that could be like way the heck up there. And then there's a slow step it has to get through in order to capture that nucleophile. So most of the time, it's tosylate on and off, and then capture to go to your product, right? So that's something we've experienced, and it doesn't, and because you have to have this rapid pre-equilibrium, the kind of climbing analogy or the flow analogy doesn't really account for this kind of a thing. The rate is still going to be mostly determined here, but it's kind of the sum of this one and this one because it determines how much of that concentration, how much the carbocation is actually going to be present. Bad eliminations, kicking out a fluoride. You know, we've said this before that fluoride as a leaving group is second year, do not permit, we can't allow it. No, it can't happen, it's just super slow. So deprotonation to make a relatively unstable carbanion that then has to kick out a fluoride. You again have that rapid equilibrium where most of the time is just acid base and then eventually kicking out fluoride being slow. Nucleophilic aromatic substitution, everybody's favorite second year reaction. Aromatic group plus like a sulfide or a nitrate or something like that, right? Nitration of aromatics goes to rapid on and off of your electrophile nucleophile pair where you have slow protonation and collapse to reform that aromatization. Those all have this same kind of point. Or things like these fragmentations. So diketones that undergo nucleophilic addition to make your sort of your sp3 intermediate, you have two choices. Kick back out the hydroxide or break your carbon-carbon bond, rearrangement. Sorry, this is like a Beckmann rearrangement or a Pinnacle rearrangement. If this collapses down, you can migrate your aromatic group over to your other center. And that's, again, you've got this relatively fast equilibrium and this on and off with a slow migratory step here. So a lot of sigmatropic arrangements follow this too. We see, and what's interesting is most of the sort of classical organic chemistry that we do that have to form these high energy intermediates have this kind of a pattern. This is back to, again, if this was your surface, what's your rate limiting step? By inspection. What would you say?
Either I1 to I2 or I5 to.
Yeah, I think it's going to be some combination, right? This may have the highest overall barrier, but you're probably going to see a large buildup of these two. Nice thing about having intermediates that are maybe as stable as this is by measuring what those intermediate concentrations are, you can reconcile all of this. And this is where intermediate measurements allow us to sort of talk through it. But again, take a look at that paper. We'll talk a little bit more on Monday, and we'll use those examples as things we can actually model. So back to like intro kinetics, this is what you guys should have all been taught. First step being rate limiting versus kind of second step being rate limiting and how you treat those two. The first one is dead easy. This is where if the first step in a reaction is slow, we have a two-step process that we can say is like, okay, step one, A with our first constant gives you an intermediate. Intermediate, second constant gives you product. And as long as this K1 is very small, so again, remember, grounding. Small k equals faster, slow rate. Slow rate. Smaller k's, slower rate. Higher k's, fast rate. Bigger barriers equal smaller k's, right? Those are inversely proportional. That's our Arrhenius equations. So the approximation we usually do, if the first step is rate determining, we say that this is the only thing that matters. After that, it's all downhill. So if we can measure just this first step, just the consumption of my starting material, I can solve the rate equation for this part. So we just simply say, well, first step is fast. The rate of that first step is going to be K1 times A. So we take this individual elementary step, and by inspection, we draw the rate equation for that one. That's the rate of the reaction. The second step is, again, elementary step. Intermediate concentration times K2 gives us this guy. But the approximation we make is that this step is an inconsequential. First step rules the game. The rate is approximately equal to just the first step. So we're kind of saying it's just looking at the rate of consumption of A and whatever that K1 is. Again, at extremes as they transition, it starts to break down, but that's a pretty good approximation. And this is what we use a lot in enzyme kinetics and stuff too. So easy, rate determining step is there. And we're saying that by measuring this K1 experimentally, we're actually getting a direct measurement of that K1. That's great. This is where it breaks a little bit harder. Yeah, sorry. Yeah, like how big do those two have to be before it splits? That is the topic of your first assignment. Once you have quasi, you can interrogate this one directly. Rule of thumb, 10x. But what you can actually what you can do is you can build a model where you have a slider where you play with those two numbers and you can see at what point does the ratio of those two start to approach a limit where K2 starts affecting the overall rate. But in general, if K1 is about 10 times K2, this holds. And again, that's 10 times. It's a relative value, so it's not an absolute number of that. It's the ratio of the two of them, or the multiplicative ratio of the two of them. Yeah, the first fun part with all this is you can start to actually answer those questions yourself by doing synthetic data. This is the opposite. This is the kind of, again, the flow analogy one. So these are, again, relatively unstable carbanions, carbocations, rearrangements. Most of the time look like this. Enolate chemistry. This is all this point too. In this case, we do that same sequence. We can sit there and say, all right, the first one is a fast equilibrium. The second one is a rate determining step based on our size. So the overall rate, again, by inspection, we said that the rate is just K2 times intermediate. In the same way that the first one, if that was slow, the overall rate is K1A. The problem with saying, oh, that's easy, it's just the intermediate concentration times K2. Most of the time, we can't analytically measure that. So it's kind of useless to say, well, it's just the intermediate concentration. So this is where we have to come up with an approximation and things like steady state and other components to make an assumption or a relative guess for what that intermediate concentration might be mathematically represented back to your mechanism. This is where you start to fuse those pieces together. So how do we do this? One of them is what's called the pre-equilibrium expression. If we assume that this is a fast equilibrium, I can express this first step as an equilibrium constant, not a rate constant, so capital K. And if you remember, if I have some equilibrium, capital K is equal to products over starting materials, right? This is what we did for acid-base reactions and things like that. We can say that if I knew the individual concentrations of these two, I've got some ratio. And we can re-express that as capital K is equal to A. So we're just multiplying algebra to put our concentration A. The reason we do this is we're just trying to rearrange a term to express our intermediate concentration. So really all we're saying with this point, with this equation, if I assume this is at equilibrium all the way through the reaction, here is a first year concept for how I can express an equilibrium, and by rearrangement I can get a simple term, in this case the equilibrium constant at A, to show a value that I can sub into another equation. I've expressed my intermediate concentration based on whatever that equilibrium constant is and my initial concentration of A. So we take that, we jam it in there, there's your capital K, and then what we do there is we say that we have these two constants. In this case, it's the rate constant, K2, and the equilibrium constant. By multiplying those together, you see K obs. So this is a very common thing that we do, and all we're saying there is, if this was a carbocation formation, it's the equilibrium constant to form that carbocation, that's our capital K, and then however fast that second step is. This is really useful because if I can measure by DFT the relative energy of, let's say, my starting material and my intermediate, I can come up with a pretty good estimate for what that equilibrium constant, the capital K value, might be. So you can take any structure and say, well, if I'm assuming I'm forming this rapid equilibrium, DFT can give me a relative energy between those two. If I know that relative energy, I can kind of work out what the equilibrium constant would be, and I can jam it into an equation like this-ish, right? So it's a very accessible way to do it. Any questions on that? The other big one is steady state. And the way to think about this is these are not exclusively two different approaches. The steady state approximation is kind of, think of that as much more, that is the ground truth of any mechanism. If you want to go down to basic fundamentals, does anybody code of any kind? Okay, you? Any other point? This is machine language. Like, steady state approximation is the ground state, like, truth of any system. So it's a little bit more complicated, but it's almost always true. It's a better approximation that covers more different scenarios. The problem with something like a pre-equilibrium simplification like this, you better have a past pre-equilibrium. If this first step doesn't operate at an equilibrium point throughout the course of the reaction, this analogy breaks down. It might be true for a small piece of a reaction, very early or very late, but it's not true over the entire course of the reaction. Steady state is a better analogy that just says, we are going to assume that the concentration of that intermediate stays constant throughout the course of the reaction. So it builds up, and then it's running constantly through the course of the reaction. So again, I just want to emphasize, the two different simplifications we apply are not like, oh, you can choose, blue pill, red pill. They're kind of the same idea, but they have different qualifications for when they should be applied. Pre-equilibrium should only be applied if you actually have a fast equilibrium. Steady state should only be applied if the concentration is relatively unchanging, right? But even then, this is real data from certain reactions. Does that look like you should be using steady state? Remember, what we're saying with steady state is d intermediate dt, the change in the concentration of intermediate against time, is 0, which means we should hope it's a straight line, right? It's not changing. Anybody who's done this, you'll see that it most of the time has got a little bit of a slope to it. There's never a case where it's perfectly dead level. So reality does come in. And what happens is there's a point in the reaction, in this case here, very often, this initial part here, almost always is where steady state is the worst, because that's when you're building up the intermediate. That is not where a system is steady state. So usually, again, rule of thumb, the first 15 to 20% of any reaction is when it's kind of warming up and getting going. So treating that early data is dangerous because the system's kind of finding steady state yet. Steady state happens in this later point. And then at the end, you have what's called terminal kinetics. It's how the reaction falls apart in those last couple of turnovers when you're really, really reaching for over turnover. So steady state is really good in sort of the heart cut, call it like 15% to 85% of a reaction. So once it's up and running, you're looking at the kind of the chunk in the middle. Now there are 4 simple steps for how you use the steady state approximation. It's something I want you guys to practice if you haven't. So when was the last time you had to draw out rate equations longhand? Last term? Okay, so you should be awesome at this one. It's algebra, so go slow. I don't know if you guys are really good at algebraic proofs. It's not one of my fortes. I'll show you some tools that I use to help you get through this. No joke, I like to write out things longhand in paper. I have journals. One of my early journals when I started doing my research was this leather-bound notebook where I did longhand proofs of these stupid things, where some of them is multiple pages of just bad algebra. And now we have Python and ChatGPT, and I could not be happier. But these are the steps you have to do no matter how complicated it gets. Step 1, write the rate law of the final step. So anytime you're doing a proof, work backwards. You say, however many steps I have, I care about rate of formation of product, so I'm going to draw the rate equation that talks about the formation of product. And you may have to, by chain, go all the way back. Every step in the system you have basically a rate equation for. Individual steps. Number 2, you describe every one of these d intermediate dt. So if there's one intermediate, you only have one equation. If there's 5 intermediates, you'll have 5 equations that are all sort of talking about how those things progress. Remember, when you're drawing a rate equation, we're saying the formation of A. So this first step here is represented in that term. This minus k1 int is the destruction of, or the destruction of that intermediate. So we have positive terms if we're talking about the formation of that intermediate. We have negative terms if we're talking about how the intermediate is being used up. So these three terms here correspond to the formation, the destruction, and the destruction of that intermediate in three different steps. Yeah, it's just follow it along. After you have all those, you're saying that the intermediate, d intermediate dt is equal to 0. If we set it equal to 0, we just have to rearrange things so that we can isolate the intermediate. So that's just, that goes on that side, divide through by whatever. But we get this complex term here, which is just isolating our x in this case. Once you've got that isolated, you go back to your original equation. K2 intermediate was our rate. We sub in this into intermediate. Bloop goes in, and that gives you your overall one here. And if you notice, the only difference between doing this steady state, the rate is expressed as a bunch of constants multiplied by concentration of A. The only difference here is these are all little k's, right? It's the individual rate forward, the individual rate back, and the individual rate to your product. Versus here, oops, where was it? Yeah, k obs here. It's just an equilibrium constant. So they're just very similar, different expressions of really the same thing. From pre-equilibrium, you're saying rate is equal to some capital K, some little k, and then concentration of A. In the case of steady state, oops, wrong way. Steady state, all we have is a bunch of kinetic rate constants, little k values multiplied by that. So they have really the same form, you're just dividing up those different pieces. This is a little bit more explicit because you've got you can kind of tune those individual k values differently. So that goes back to what I was saying about how they're really the same thing. So that's how we take a multi-step reaction under equilibrium. Michaelis-Menten is our approximation for doing rate equations on catalytic systems. It's really the exact same process where we have a multi-step transformation, substrate plus enzyme makes an intermediate, and it's a fast intermediate. That intermediate then goes through a second step to make a product and regenerate our enzyme. So the only difference between our previous example and we start talking about catalysis is that you both use up and then return a part of the reaction. There's something that's being recycled. So don't look at this as it's got to get so much more complicated. You've just added a term here to your output of your reaction that just has to be added into the math that you push forward. There's only one other complication that goes into this too. If I had to express, let's say, the concentration of my enzyme, remember when we talk about a rate equation, the rate equation has to be concentrations of things that you could weigh out and put in the reaction. So that includes your starting materials and your catalyst, the thing that you weigh out. So when we say catalyst, we mean pre-catalyst, the thing that you would weigh out, palladium acetate, enzyme, throw it in the system. ES is consuming part of your enzyme. The intermediate concentration here, your enzyme, what we actually throw out is actually split between free enzyme, what we call E, and your intermediate. So the total catalyst that I throw into the system is equal to free enzyme and any intermediate that might have bound that enzyme, or free catalyst plus any intermediate that binds the catalyst. So why this gets more complicated is we need the mass balance equation. It's exactly the same steady state derivation that we've done before, the same thing as like the individual steps. Instead of just having to do the 4 steps that you saw previously for this derivation, you now must also add in this enzyme total or catalyst total is equal to all intermediates plus free catalyst. And then that allows us to actually solve for the, to isolate a term for the total catalyst in the system. The reason why, again, is when we do a reaction, when we charge in the catalyst, we know total catalyst. We do not know free catalyst concentration or the intermediate concentration. So we need this extra one to go through. If we go through all this, then you get a more complicated equation, a whole bunch of math later, and you get that. And then dividing into the denominator, we end up getting our more classical one. The actual one that we do for if you've been a biochemist, is that's the Michaelis-Menten equation that we usually express. We have a capital Km value where all we did is take this part of the term here and just re-express it. And the reason why we use that is the Km value is a binding constant that we can apply. It's something that, again, if you're qualifying enzyme affinities, it's an important value we can measure, but it's made out of this sort of a term. Again, I've got a longhand derivation of how this part comes up. I do not expect you guys to play with it because I'll show you some tools where you should be able to derive it longhand. Now, why this matters. If I gave you something like one of these equations, embedded in this equation is everything we need to know about, is this a first order process, a zero order process, second order process, everything we talked about that part. The rate equations we talked about experimentally in the first class, or yesterday's class, are really no different than this. This is just the theoretical rate equation based on the equations that sort of describe the mechanism that you're talking through. The difference is, or how this part varies is, depending on the concentration of where you are on that curve, it's going to simplify to one of two possible outcomes. In other words, this is the truth for any mechanism. Doesn't matter what it is, every enzyme will follow this Vmax S, capital Km S type equation. If we're really large substrate, so we've saturated the substrate, this denominator value is absolutely massive, it means that the Km value doesn't really matter. You can simplify this denominator by saying, I'm going to not pay attention to Km. It's really S is huge. So this goes back to the pseudo zero order, pseudo first order stuff we talked about last time. If that's true, if I can simplify this denominator, I can now cancel out my S. And the rate of product formation, this equation simplifies to dp dt is just Vmax. I can cancel out all the other junk in between, and the equation gets simpler. On the other side of the equation, if S is really tiny, we can neglect it, so it disappears, and now we have Vmax Km S. So we use this all the time because in the end, if I looked at this here, d product dt equals Vmax, what is the order in A, in your substrate, if this is your equation? Zero order in A. It means changing A in a case, or changing the substrate concentration in this regime doesn't do anything to the rate of product formation. We're already so high in S that adding more S doesn't matter. Where a little depletion of S is not going to change the rate of the product formation. It's just Vmax. It is a zero order process. The exact same mechanism at a different concentration in S will simplify here. So what's the order in substrate when we're under this one? 1. The part I'm trying to put under is order, especially when you get to catalytic systems, is not a holy number. We cannot look at this and say, I did this measurement. If I do the measurement under some substrate concentration, this is what I'm going to measure. And if I did that measurement and I said, well, based on those measurements, my catalyst is zero order in substrate. That doesn't mean it's zero order in substrate for every single possible experiment you might run. Likewise, if I do an experiment under very low substrate concentrations, I'll see first order in substrate. Both are true, but this is back to, again, so have everybody seen a lion before? At some point, maybe not in person. Have you ever seen a person put their head in the lion's mouth? Never been to the circus? Wow. Point is, your conclusions about what a lion may or may not do to you depends on where you look. If you are in the middle of Africa and you're like, well, I saw this at one point, you know, in a circus and there's this trained lion, the guy put his head in there, I think I can do that too. That may be this circumstance. Your environment dictates the outcome. Does everybody recognize this from enzyme kinetics? Do you remember at this point? This is the rate of reaction against substrate concentration. This is what we call Michaelis-Menten plot, right? Ish. This is what everybody who ever does enzyme kinetics does. This is not a reaction plot. This is not reaction progress. This is, I do a reaction at some substrate concentration, and I measure the initial rate, and I put a dot down. Then I increase the substrate concentration, measure the rate of reaction, put another dot. And you do many, 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 many of these to create this process. Sorry, what was your question? Yeah. 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 No, if S is very large, the rate does not change as S is changed by a small amount. Oh, okay, sorry. There. Let me do it here. So this is your fundamental equation, right? If S is very, very large, what I said is the denominator, which is normally Km plus S, right? I'm saying if S is huge, it is so much larger than Km that I can simplify this denominator to say it is not, the denominator is not Km plus S, but it is approximately equal to just S. I'm neglecting K because S is the big deal. And if that's what the denominator is, if the denominator is just Vmax S over S, S is gone. Cancel, cancel. Equals that. Good? No problem. Point is, this is a whole bunch of individual rate measurements as you walk up the substrate concentration where you're holding the catalyst concentration constant. The same enzyme, the same mechanism can show first order behavior in this regime and zero order behavior over here. The thing I'm trying to underscore is, and for people that have done like, I will do kinetics and that'll tell me my mechanism because I'm going to measure the order in my substrates, whatever, it'll tell me everything. That's a lie. It depends on what concentrations of your other species are in the system. And the same mechanism can actually show many different possible orders. It's what's called sensitivity. The reaction is very sensitive to substrate concentration down here because of the values of Vmax and Km. It's very insensitive to the concentration of substrate up at this edge over here. So order is not just, oh, I did a reaction, it's a Suzuki reaction, it must be first order in substrate. No, it depends. We're going to walk through this part next class. Yeah?
So when you're talking about substrate concentration, when you say very large, very small, relative to the catalyst?
It's relative to the catalyst. Exactly. It's a ratio problem. In this case, if I need the reaction to go faster, what's happening here, this is a traffic jam. If I have a ton of substrate, but I don't have enough catalyst, it's spending all of its time waiting for the catalyst to be free. Adding more catalyst will make the fundamental rate go faster, but remember, the rate that we see is kind of normalized by catalyst concentration, so adding more doesn't make the fundamental rate constant faster, it just makes the observed product formation faster because you just gave it a bigger highway effectively, right? Okay, sit with this. It may suck. I want you guys to, again, go look at that paper. We're going to practice some of the derivations. It's going to be important for you guys to be able to actually do things like those manipulations, the algebra to solve it. I would challenge you guys, please go through the derivation of the Michaelis-Menten equation. You should be able to write this out and do the algebra for it. If you have any problems with it, I've done this many times. I've got videos on the whole thing, but I can help you through that derivation. All right, I'll see you guys